Hi everyone. So what we're going to look at today, as the title suggests here, probability tree diagram. So previously we've looked at three distributions, um, binomial, Poisson, and a normal distribution, and they all involve formulas. But the normal distribution, we actually use a kind of graphical method to illustrate where we're looking at the probabilities. And so probability tree diagrams, um, it's actually a good method that we can use, as I say, to illustrate them. So there you go, tree diagrams. Oh, what do they mean by that? Well, we're looking at branches. So branches are like you can go up one branch or up another branch. So that's like decision making. That's what we are sort of talking about. It's like a yes, no, head, tail. You go one route or another, and then once you reach the end of a branch, that might divide into two or more branches, so that'll be other routes you can go down. So that's what we're saying here. So anyway, if you were in class, we had a nice little PowerPoint, so I'm just going to go for that there and see if it explains it to us just as well as myself. Okay, right. These learning objectives are BARTs. So the and or rule that'll come into its own. Don't get too hung up in learning a rule. That's what we want to be able to do. Draw a tree diagram and calculate the probabilities. That's what we are interested in. Right. Okay, so they're given as a typical example um, here. A coin is tossed and a die or a dice is rolled. And seeing that they speak about the sample space, that's everything that can happen within this scenario. Okay, so everything that can happen here is to do with the coin, head or tails, and to do the dice or the die. There's 6 faces numbered 1 through to 6, so that's everything that can happen. And 6 times 2 is 12. So there's 6 kind of possibilities or outcomes. Okay, so it looks like they're highlighting in red in the bottom corner 6 and tails. So I reckon that's what they want us to calculate here. Oh, and there is. What's the probability of getting a 6 and a tail? Well, they're saying it's 1 in 12 because that is the only box, 6 and T, out of the 12 boxes from the sample space. So it is 1 out of 12. Okay. Right, there's been about 2 events happening. Right, that's what we kind of looked at there. So getting a 6 on the die, 1 out of 6. Getting a tail from the coin, 1 out of 2. And for both of them being coincident, getting a 6 and a tail, it was 1 out of 12. So they're trying to get you to spot the connection, get the link. So they're saying it's a 6 times a 12. That little asterisk they're using there, they're trying to suggest that's multiply. That's fine. probably use that in Excel. So it is 1 out of 12. So when it's and, we multiply the individual probabilities. Okay. So that's what I'm saying there. If it's and, multiply probabilities. If it's or, you add them. And what you'll find with tree diagrams, it's when we get to the end of the branches and when we get our final probabilities, if there's more than one option that something will happen, we will add those probabilities. Okay. Talking about fractions and percentages. Yep, fraction. A percentage is a fraction. Okay. Sometimes a fraction can be written neatly as a decimal. That's fine. But in certain circumstances, if it's something like a third or 6/7, you can't write that nicely as a decimal. So we might leave it. And I'm emphasising here that probabilities take on values between 0 and 1. Okay. Right, our tree diagrams, and I know you can read, so I won't read it to you. So our branches represents the decisions. Okay, so when we go along one branch, then we might have 2 or more other branches coming along, so we have to travel along those as well. So we're just going to go for an example here of what happens if it rain. For instance, on a Monday, the probability is 0.2, 20%, and assuming the Tuesday is the next day after the Monday, they're saying the probability that it will rain is 0.3. The question here is, what is the probability that it will rain on Monday and Tuesday? So for this here, we need to look at Monday first. So one of the easiest options is to use the tree diagram. So Monday. Okay, so what are the options for Monday? Well, there's 2 things that can happen on Monday. It rains or it doesn't rain. Okay, so the upper branch here is going to rain. And it was stated earlier that the probability was 0.2 or 20%. Well, that's if it rains, but what if it doesn't rain? Well, we need a probability for that there. And so all the probabilities I have to add up to give us 1. So that should be 0.8. And like you can see there, they're just emphasising that they always add up to give you 1. Okay. If there was 3 branches there, 4 branches, all the individual probabilities for the branches would have to give you 1. Right, so that's Monday accounted for. If it rains, 0.2, if it doesn't, 0.8. Let's move on to Tuesday. Right, so these upper 2 branches that we're just seeing here, this is now assuming it rained on Monday. So it rained, it was 0.2, so we're moving on to Tuesday. And for the Tuesday, if it rains, it was 0.3. And if it didn't rain, it was 0.7. So we're just putting in those probabilities there. And yet again, those individual probabilities add up to give you 1. So what we're doing there is we're going from Monday into Tuesday. But on the Monday, if it didn't rain, with a probability of 0.8, we now have to enter the lower 2 branches. if it rains or it doesn't rain on Tuesday. So again, the probabilities are the same as above, and yet again, it adds up to give us 1. I'm sure you figured that out. So that there is your tree diagram for Monday followed by Tuesday. It rains, it doesn't rain on both days. So this is making up our minds. This is our decision tree probability tree diagram. So let's go through the different options. It rains on Monday, followed by it rains on Tuesday. So what we're doing is we're just following the path here. And what we're going to do here is we're just going to multiply each of the probabilities if it rains on Monday and it rains on Tuesday. So we get 0.2 on the Monday, 0.3 on Tuesday. So just multiply them together and hopefully we get 0.06, which we do. Okay. Let's now move. Oh, we're still on Monday, but what happens on Tuesday if it doesn't rain? So we've got 2 probabilities, and again, just multiply them together. Just go down the 2 branches, and that will give us our overall probability that it rains on Monday and it doesn't rain on Tuesday. Okay, we're done with Monday. Let's move on. We're done with Monday if it rains. Let's move on to see what happens on Monday if it doesn't rain. Okay, we're going down that branch there. So it doesn't rain on Monday, 0.8. So we've got 2 choices here. What happens if it rains on Tuesday? You get 0.8 times 0.3, multiply them together, and that gives you the overall probability for it not raining on Monday, but it rains on Tuesday. There you go. Right, lastly, if it doesn't rain on Monday and it doesn't rain on Tuesday, again, take the 2 probabilities, 0.8, 0.7, multiply them together, and that will give you your overall probability for it doesn't rain on those 2 consecutive days. And yet again, we've taken the probabilities for each of the pathways or branches, and guess what we're going to do with those numbers? Yep, you're going to add them up, and guess what you're going to get? 1, as always, because the sum of all probabilities in the given scenario always give you 1. Okay, so we've just finished with that little PowerPoint there, which I thought I think I explained it quite well. So let's see if I can do any better. I actually included the PowerPoint here in the video because I know sometimes some of you can't access PowerPoint, but you should be able to download it. Anyway, let's move on. Oh, let's deal with dice or die again. So what's going to happen here? So we're going to have some kind of scenario here. And the scenario is we're going to roll a die or a dice, one after another. And what we're looking at here is what's the probability of it landing face up on both occasions. And they want us to calculate this probability. So there's many ways we can do it. We've done it in the past with basic probability. So what we need to know is actually the individual probabilities probability of getting a 4? Well, you know there's only 4 out of the 6 faces, so that's 1 out of 6. And the probability of it not being a 4, well, that's a complement of that. So that's the 5 other faces. But I'm going to change the notation here. I'm going to put a little bar over the 4, and that will mean not 4 for us. So if everybody's happy with that, then we can move on. So probability of not being 4, that'll be 5 other faces over 6. Right, so we'll get the 2 probabilities there. They will relate to the 2 branches, the 2 decisions. There's the first one. Second one, is it going to be a 4, 1 over 6? Or is it not going to be a 4, 5 out of 6? Okay, so that's on the first row of the die of dice. So then we have a second go. So if we threw a 4 initially, then we would move on to these 2 other branches. Well, what's going to happen next? A 4 or not a 4? Probability of 6, not a 4, 5 for 6 again. Downstairs, what happened if through not a 4? Yet again, identical. Only 2 options for the second one. It's going to be a 4, it's not going to be a 4 with the same probabilities. Right, so going along the top line there, top branch, 4 or 4. Next one, 4, then not a 4, and we're indicating that in the bracket notation. So that's dealt with throwing a 4 initially. What happens if we don't throw a 4? Well, that means we've got 2 options after that, a 4 or not a 4. So up there, you can see just following the pathways, not a 4 followed by a 4, and finally, not a 4 followed by not a 4. So, what we're doing here in order to calculate those probabilities, like you saw in the PowerPoint, 4 followed by a 4 was 1 6 by 1 6. We're just going to multiply them together and hopefully get 1 over 36. Other option, throw a 4 first, not a 4. Take 2 probabilities, 16 5 6, 5 over 36. Moving swiftly on, if you threw a not a 4 first of all, followed by a 4, just multiply the probabilities together, 5 16 6, 5 over 36, and finally, not a 4 followed by not a 4, 5 16 5 6, 25 over 36, there you go. Right, that's our tree diagram with the associated probabilities. Right, so going back to the question, we wanted to know what was the probabilities of 2 4s landing face up. So let's go back to the tree diagram. 2 4s. So there you go. We didn't create this tree diagram for no good reason. So we just go straight to there and go straight to the answer. That's why we created this. So the probability of getting a 4 followed by a 4 is 1 over 36. Okay, we're going to have maybe a few more questions here. So what would be the probability of throwing no 4s face up? So that was like the 4 with the little lines above it. And another question, what's the probability of getting at least 1 4 face up from 2 throws? At least 1 4. Okay, so there's a tree diagram there with the associated probabilities. So there's your no 4s. So there's only one option there. Not a 4 followed by not a 4 is 25 over 36. And that's the answer. That is you. At least 1 4. Well, at least 1 4. That might suggest more options. So up there, well, there's 2 4s there, but there's definitely at least one. Down below, I can see a 4 and not a 4, but definitely at least one 4. Downstairs again, there's a not a 4, but there is a 4 there. And the bottom one, well, they're both not 4s, so we don't count them. So we've actually got 3 options here, 3 possibilities. So what we're going to do is just take the probabilities for each of them and sum them up. Okay, so there is 3 possible outcomes here that we are going to sum. So I've just highlighted them there. I'm going to sum them, so add them up. So at least one 4, and just taking the notation that we were using there in the tree diagram. 2 4s, a 4 not a 4, not a 4 and a 4, but in each of them there is at least one 4. And there's our 3 individual probabilities. Add them together, 1, 5, 5, 11, and it's all over 36. Just leave it as a fraction, that's fine. So there's 11 chances out of 36 that you'll get at least one 4. Okay, let's moving swiftly on. Just change the topic here. So there's a bag with 3 cotton balls, and so we're going to construct a little tree diagram here, just to show you what happens if you select 2 balls from the bag, but we actually replace the balls. So just a wee demonstration here. So if on the first pick I was to choose a blue, I would note that down, but then I put it back in. Okay, and whatever happens next, so that means I've still got a total of 5 balls in the bag. Okay, we'll deal with without replacement at another time. So yes, so this is putting them back with replacement. So we've only got 2 options here. You pick a blue or you pick a red. So if you pick a blue, pick a red. For the blue, there's 3 blues out of 5 total. For the red, there's 2 out of 5 total. But remember, put the balls back in before your second pick. If you picked a blue initially, put it back in. It's going to be the same scenario. There's still going to be 3 blues and 2 reds. So our probability stays the same. And downstairs, on the red, if you did pick a red initially, the probabilities for your second choice are going to be the same. On the top, the pathways are blue, blue. Okay, and multiply your probabilities together. Next, it would be blue followed by red. Multiply your probabilities together. Moving on, red, blue. Multiply your probabilities together. And finally, red, red. Multiply your probabilities together. That's your tree diagram with your combinations, your picks, blue, 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 red, blue, red, red, with the associated probabilities. 9, 6, 6, and 4 add up to give you 25 over 25, which is 1. So here, what would be the probability of selecting a red and a blue, or a blue and a red? The wording of this might be strange, but we don't. I'm trying to emphasize the word or here, because or usually means there's more than one probability that we can add together. So forget about the and rule, because the red and the blue and the red, it's really, it doesn't matter for us. As long as we got a red and blue, or a blue and a red, in whatever order, it doesn't matter. So let's go back here. So what are the options? There's a blue and a red, or a red and blue. And secondly, so that's that probability, 6 over 25. Next one, red or blue, blue and a red. The order does not matter. And again, the probability is the same. Is that unusual? I don't know. Well, I do know, but I'm asking you. Take those two probabilities, because there's more than one option here. Add them together. So the probability of red and blue, or a blue and a red, is 6 over 25 plus 6 over 25, 12 over 25, and oh, that would come out as 0.48 or something like that. Leave it, just leave it as a fraction, that's nice. Okay. So following on from the PowerPoint scenario, we're dealing with dice and coins, stuff like that. We dealt with the dice, we dealt with the balls. So let's go for something more sciencey. So what we're talking about? So we're talking about some kind of epidemic, some disease. 8,000 animals were tested for this disease. 1,000 were female, 400 were infected. The remainder were male, of whom 10% were infected. So they're trying to get you to do a little bit of arithmetic here. So how many were male? Well, 8,000 take away 1,000 female, so there's 7,000 going to be male. 10% infected, and that's going to mean 700. So we've got that there. So you see we're told 8,000 female, 1,000 male, 7,000 females probability of being infected. 4 out of 10 fifths males, 10%, 1 out of 10. And on the right hand side, that's a probability of selecting our males or females. So here, there's a probability for selecting a female or male from the group. And if they're infected, for females, that's a probability, but I think I'm going to keep it as over 10 here, because when I go to the males, I can see that that's over 10. I just like to keep the denominators the same throughout the problem, right? And it avoids decimalisation, and it avoids confusion. It's my job to confuse. Okay, let's move on. So, a couple of things here. Draw a probability tree using the data. That's fine. Then we'll deal with question B. 2 branches, male or female. Female, 1,000 out of 8,000, 1/8. Male, 7,000 out of 8,000, 7/8. If they're infected or not infected, okay, so the I, the bar over I to mean not I, in both parts. So for the females, it was 4 out of 10 for infected, not infected 6 out of 10, they had to give you 1. For the males, it was 1 out of 10 for infected, so that means not infected, it's 9 out of 10. Okay, so let's get our notation sorted out. Female infected, along the branches, 8 times 4 tenths, 4/80s. I know that can get simplified, just leave it. The next route, female followed by not infected, 8 times 6 tenths, 6 over 80. I'll just leave it like that. Next, I'm going down the male route, male infected. That's 7/8 times 1/10, 7 over 80. That's fine. And finally, male and not infected. So that'll be 7/8 followed by 9/10. There we go. So can we just add these together? 63 and 7. I'm just going up from the bottom here. Is 70. Add 6 is 76. Add 4 is 80. So I've got a grand total of 80 over 80, which is indeed 1. Okay. Part B. Determine at random the probability of selecting an infected female animal. Infected female, or female who's infected. So from the tree diagram, female who's infected, it looks to come up there. And the reason we created the tree diagram is so we can see the actual numerical value, which is 4 over 80. So the probability of a female infected, 4 over 80. If you want to simplify it, 1 over 20, or decimalize it, if it's nice, is 0.05. That's fine. That looks okay here. Right, they're trying to complicate things now. So I hope you've took that on board. So for some reason, they're carrying out a second test. And that is used to determine whether an infected animal needs to be destroyed. I know that's horrible, but they're just going for that. So it needs to be destroyed. So what they're saying here is 80% of the females and 30% of the infected males, both infected, need to be destroyed. Then what is the probability that an animal selected at random has to be destroyed? So we'll go back to that tree diagram, and they're talking about being infected on both sides here. So what I'm going to do here is I'm just going to look at the infected branches here, and then I'll trace that back to both females and males. But then we have probabilities of being destroyed and not destroyed. So I'm just going to add 2 new branches to both the infected parts. Okay? Destroyed and not destroyed. So for the females to be destroyed, it was 80%. For the males, it was 30%. So I've just expressed them as fractions there, 8 over 10 and 3 over 10. Put them on the diagram there, but I'm only interested in ones that have been destroyed here. So I just need to put that down. And go down to the males, 30%, 3 over 10. That's all I need here. So the highlighted yellow here is the 2 pathways I'm going down. So those 2 pathways lead to 2 outcomes here, 2 probabilities. So female infected destroyed, and 8 times 4 tenths times 8 tenths. Got that there. Yeah. And that gives you 1 times 4 times 8. Was that 32 over 800? That's fine. I'm not simplifying it. And the next root is male infected disease at 7/8 times 1/10 times 3/10. 71 times 3, 21 over 800 in the bottom again. 21 over 800. There you go. So I've got 2 possible outcomes there. So just take them. So the probability of an animal being destroyed here is the sum of those 2 probabilities. 32 over 800 plus 21 over 800, 53 over 800. You could leave it like that, or you could decimalize it. 0.06625. So, as I always say, rewind here, because there was quite a lot going on with these tree diagrams. Okay, so I think I'm going to leave it there, and I'll upload that onto your team channels, and hopefully you can make sense of it. But I do like feedback, positive or negative, okay? And you can put it in the form of a tree diagram. Okay, right, bye for now, folks.